the first practice problem I had posted on SmartSide. In this case, we're just going to go through some structures I found online, and we'll talk a little bit about the shape, but we're mostly, as you saw on SmartSide, going to focus on polarity. Okay. So, the general rule for polarity, remember polarity is means there's a dipole, or the uneven distribution of electrons, which can simply be seen if the molecule is asymmetric. So if the molecule looks asymmetric, then we would call it polar, or having a dipole, or having a non-zero dipole moment. If it looks symmetric, then we'll call it non-polar, okay? Or no dipole, no net dipole, a zero dipole moment. Okay. So let's take a look. Let's start with this one right there. We'll zoom in and you'll get to see all these molecules as we go through. What do you think? Does it look symmetric or not symmetric? It's symmetric, and so we would call this non-polar. If you draw out the bond dipoles, you'll see they'll cancel out. Okay? It's a fully symmetric molecule. Let's try this one right here. This one's a little bit tougher. I'll get a model while you're thinking about it. What shape is that, by the way, the molecular geometry? Has four groups. One is a lone pair, so we call this trigonal pyramidal. Well, it looks like this. Okay, trigonal pyramidal. So this trigonal pyramidals are always asymmetric, or another way to say it, they're always polar. Okay, so a trigonal pyramidal, like that one, that would be polar. Okay, how about this one? Either one, doesn't matter which one you look at it. Polar or non-polar. This is polar, it's bent, so it's asymmetric. Okay, doesn't matter that they're all oxygens. Turns out that the lone pair on the center oxygen causes the uneven distribution. Okay. First, before we do this one, what is the electronic geometry of every central atom here? Electronic geometry. Four groups on all of them, so they're all tetrahedral. Okay? The first one's bent, the second one's tetrahedral, the third one's trigonal pyramidal. But they're all tetrahedral. So it's not drawn to the correct shape. But regardless, you can probably tell that it looks asymmetric. So we call this one polar. This one's polar. Okay, let's try this one first here on the left, that one. You might not be familiar with this way of drawing things, but sometimes when we're drawing an octahedral, remember 6 groups, it would be like this. This is octahedral. Okay. Sometimes they draw a little box around one of the planes. But it's still octahedral. And in this case, they drew a bond to the lone pair. Sometimes that's done. But it's just two lone pairs on this iodine. Okay, the iodine has 6 groups and 2 lone pairs. What's the molecular geometry? Yeah, this is called square planar. Bond angles of 90 degrees. Okay, what we're interested in, though, the shape is drawn. Is this polar or non-polar? It's symmetric, so it would be non-polar. We would say it has no net dipole, and we would say it has a zero dipole moment. Okay, all those would be synonymous as far as we're concerned. All right, here's a tougher one. This one, polar or non-polar? Yeah, this can be a little tough looking at it right now. What's the electronic shape of this? Electronic geometry. That's 5 groups. Trigonal, bipyramidal, and the molecular geometry would be called seesaw. So really, in order to answer the question, you should draw the shape, which is on our second page actually. This would be the shape of it. And you can see this shape would, it looks asymmetric. It is, so we would call this one polar. another set of tough ones down here at the bottom. This one is 6 groups on that center xenon in both cases, on the right and the left. So this is also octahedral, and the molecular geometry would be called square planar. Okay, one of these is polar, one is not. Is the polar one on the right or left? The polar one's on the left. You can see it's asymmetric. There's fluorines on one side and fluorines on the other. However, in the case of the one on the right, this would be non-polar because the chlorines are equal and opposite to each other, and the fluorines are equal and opposite or symmetric to each other. So the one on the right is non-polar, the one on the left is polar. Okay, let's try another one. How about this one right there? Right there. What'd you get? Okay, I had some people say polar. I just want to do a different possibility. What if I had drawn this? And I'll put in all the lone pairs. What's this one? Think about this one as I put in the lone pairs. Is this polar or non-polar? The one on the top. They're both actually polar. Why is that? What is the shape of this? 4 groups is tetrahedral. So you actually, unless you're imagining it in your mind, you could not determine polarity from what's drawn here, because you have to imagine something like this. Okay? And 2 groups, there's 2 sets of groups that are the same. So I'll put 2 big blue pieces here and 2 smaller white ones. You can see that when it gets in the tetrahedral shape, it must be polar because it's asymmetric. On one side, it'll have 2 of the groups, and the other side of the molecule will have the other 2 groups. This has to be polar. In fact, a tetrahedral molecule will always be polar unless all 4 groups are the same. Okay, so unless all 4 groups are identical, it's going to be polar. And so it doesn't matter how you draw it in 2D space, it's really a 3D entity, and it's always going to be polar. Okay, let's do this one right here. This one, arsenic one. Okay, polar or non-polar? This is also going to be polar. It has a dipole. The reason is it's asymmetric. It's the T-shaped molecule is always going to be asymmetric because there'll be a chlorine in this example on the right, but no chlorine on the left-hand side. There's lone pairs on the left, but no lone pairs on the right. Okay, we did this one on the right. Let's do the one on the left now. I'll ask it in a different way. Does this have a 0 dipole moment? Yes or no? No. This dipole moment is non-zero, which is another way to say it's polar or has a dipole. Why? Well, it's square pyramidal. That's the molecular geometry, square pyramidal. And you can see there's oxygen on the top, but not one on the bottom, so it's asymmetric. This is polar again. Okay, we did this one. That's a copy. Let's do this one right there. Okay. Does this have a net dipole or no net dipole? Net dipole or no net dipole? This has a net dipole. That means it's polar. That means it has a non-zero dipole moment. It's just asymmetric. Even though it has 3 pairs of 2, they're asymmetrically arranged. And then the final one I had was this one here on the bottom. This one's kind of crazy. You can't see it. The middle part is all carbons, and then attached to the carbons are all hydrogens. We, in fact, could name this from chapter 3. Does anybody know the name of this? Yes, 8 carbons, so it's octane. Okay, polar or non-polar? Yeah, it looks a little funny, but this one's actually non-polar. for a couple reasons. One is that zigzag backbone of the carbon chain goes back and forth in a symmetric pattern. The other reason you could say is that carbon and hydrogen have pretty similar electronegativities, so we consider a carbon-hydrogen bond to be nonpolar. So that makes a number of organic molecules nonpolar. Okay? So like oil, which is hydrocarbons, or carbons and hydrogens, oil would also be nonpolar for the same reason, lots of carbon and hydrogen bonds. Okay? One thing we're ignoring as we do these examples is the overall charge. Okay? Which I believe I'm going to talk about the final next time. On the last class, we'll be talking about the final. I don't believe we'll need to take that into play, but if we do, I'll let you know in the last class. Okay? All right. That was the first set of examples. I have a lot of practice of that online. I think I showed you that already, about Lewis shape polarity 1 through 5 and something called dipole moment. Okay, now I'm going to flip over to the other example. Oh, yeah, I want to show you this before we did our second example. Where that is. Last time we did MO structures, or molecular orbital, really diagrams. We did molecular orbital diagrams. And we did a couple that look like these. Okay? I believe we did H2, the one on the upper right-hand corner. This is the template for an MO diagram, where we did the one on the upper right-hand corner. Remember, every bond has two parts. The bonding part, which is the lower energy part, that's the sigma 1s in all of these. And the anti-bonding part, which is the one above, higher energy, and that's the sigma 1s star. The star means anti-bond. Sigma means the bond occurs between the center points of the atoms. And on the outside, either on the left or the right, on the outside, we put the atomic orbitals, or like 1s, 2s, things like that, 2p. In the center, we put the molecular orbitals. So the sigmas are considered molecular orbitals, or orbitals for a molecule. And so this is from your textbook, somewhere in there. And just a couple examples. This is on page 416 of your textbook. So I believe last time we did these two on the right. If we did H plus or He2 plus, we get the diagrams on the left. So what we're going to do, the one we had on SmartSite, we're going to draw the MO diagram, I believe, for lithium-2. Lithium-2. So let's try it out. So to do an MO diagram, you put the molecule in the middle, and you put the atoms each on either side, on the right and left. And then on the left-hand side, you put a y-axis for energy. And then different color pen, I'm going to write the electron configuration. So lithium is 1s2, 2s1. And I'll do it for this lithium as well, 1s2, 2s1. Okay? Electron configuration tells us how many electrons are in each orbital. Now, this is going to be a little different than some of the ones we've done already, because now we have two orbitals we're talking about. The 1s set, the set of 1s orbitals, and then the set of 2s orbitals. The procedure is going to be identical, and they're actually going to be kind of two separate diagrams. Let me show you how this works. Just like before, we're going to put two 1s energy levels, and they're going to make a bonding and an anti-bonding. Dots like this, just like we did before. The lower energy is called sigma 1s, and the higher energy part of the bond is a sigma 1s star, where there's a bonding, low energy, anti-bonding, high energy. That's how the 1s section of the diagram will look like. We haven't put in the electrons yet. The 2s part is going to be drawn directly above that. Why, and I'm going to put it higher energy. Does anybody remember why 2s is higher energy than 1s? It's based on what quantum number? The n, the principal quantum number, 1 or 2, is larger, and this will be a higher energy. If we drew 3s, it would be way up here. 4s is higher, etc. So as n increases, energy increases. Same though, 2s has two parts to its bond, a low energy and a high energy, or a bonding and an anti-bonding. Sigma 2s now is the lower one, because it comes from a 2s atomic orbital. And the high one is sigma 2s star. This should look identical to the bottom one, except that 1s is replaced by 2s. Otherwise, it should look the same. Okay? Except the 2s is higher energy because n is larger, or 2 is larger than 1. So it's a higher energy on the y-axis. So when you get into your 2s orbitals, they're actually identical to your 1s orbitals. Now, what I like to do last is put in the electrons. Okay? So the electrons, go back to your electron configuration, it's 1s2. That means there's 2 electrons in the 1s, and it's 2s1. So there's 1 electron in the 2s. 1s2 means 2 electrons in the 1s for the right-hand side, and 2s1. That means 1 electron in the 2s atomic orbital. Now, when you're filling in the electrons, I like to do one set of orbitals at a time. So let's focus on the 1s, or the bottom half first. For the bottom half, there's a total of 4 electrons, 2 on each side. So we're going to use 4 electrons in the middle for the molecule. 1, 2, and then the third one goes up here. There's no other spot on the bottom, and the fourth one pairs with it. So total of 4 down there. Now let's do the top half. The top half has 1 electron from each side, or a total of 2. And so we fill 1 and then 2. And that's it, there's no more. This would be the molecular orbital for lithium-2. Okay? The bottom half, which is what kind of electron? Everybody remember the name for the, in this case, the 1s electrons? We call those the core electrons. Top half would be the valence. Anything from the previous noble gas is called a core. So just to label this, these would be core electrons on the bottom, and the top would be valence electrons. Okay? Now, 2 things we like to ask, 2 common questions. One has to do with magnetism. So when we look at it, we want to know if it's para or diamagnetic. Look at the center, most part of the electrons, is this para or diamagnetic? You should say diamagnetic, and the reason is, over here, when you look at the center part right there, they're all paired. So we call it diamagnetic. Remember, di means 2, so diamagnetic, 2 electrons are paired. Okay, that's magnetism. The other thing we commonly ask is the bond order. Okay? The bond order, there's a number of ways you can calculate it. What I recommend is using the topmost part of the picture to do the calculation. Okay, so use the topmost set of orbitals to do the calculation. So we're going to focus right here on the 2s. Okay, right there on the 2s. The first number is the number of electrons in bonding orbitals. What's that number? 2, from right here. There's 2 electrons in the bonding 2s orbital. The next number is the number of electrons in anti-bonding molecular orbitals. That's going to be the number 0, because in the anti-bonding, the starred one is 0. So 2 minus 0 divided by the number 2, that's going to be 1. What kind of bond is that? It would mimic a single bond. So it's a single type bond. Alright, and that's the molecular orbital for lithium-2. Cool, finished our second problem. Any questions on that? Okay. Da-da-da. Okay. Sadly, we lost a holiday. And whether it's happy or sad, I don't know in your mind, but this is the eve of the last lecture. As far as lecture time goes, We have one more lecture left after this one. As normal, we have office hours there at 10:40 after this class in 3061 since it's Tuesday. All right, let's see what I was up to. What's up next? We have now, yes?
How come you don't put one student
You're asking of these two electrons, why are they both here instead of one down here and one up here? Okay, what's going to happen is it's lower energy for them to pair, even though electrons don't like to be next to each other, that's why they do the opposite spin. Then for this second electron to go up here. Now if those energy levels were really close, which you'll see an example later in class, then the second one would go up to the higher energy level. But in this case, they're not close enough numerically for them to split. So they prefer always to go to the lowest. And so in general, you're always going to put them at the lowest energy before you go up to the next one. Good. Yes? Three atoms. Then if there are 3 atoms, you would be taking physical chemistry right now, which is Chem 120. So that's beyond the scope of our class. We're not going to go past 2 atoms, and they're all going to be homonuclear, which means they're the same atom. So we're not going to go above neon, and always that 2 atoms will be the same. To go beyond that adds a degree of complexity that is beyond the scope of our class. But I recommend you be a chemistry major because you will learn all about that. Okay? But you don't have to worry about this class. I think on some of my videos online I have some advanced molecular orbitals if you want to see what they look like, just if you're curious. Okay. Now, we've done everything S. Up to beryllium is all S. Once we get to boron through neon, remember, for our class, we're not going to go past neon. We're talking about p orbitals. So now, let me introduce the p orbital molecular orbital diagram. Demo is freezing.
Basically just ways to draw that atom.
Okay, afterwards this after. Okay. Let us do an example of N2. MO diagram for N2, and this is going to be huge. So I'm going to take the whole page to write it. You know how big I write that. Okay, N2 comes from 2 nitrogens. They're 1s2, 2s2, 2p3. And it's 1s2, 2s2, 2p3. Each nitrogen, there's electron configuration. So we're going to have 3 sets of pictures here. We're going to have the 1s picture at the bottom, lowest energy. Next, middle energy is 2s, and the highest energy is 2p. So I have 3 sets of diagrams. The bottom ones will look just as you're familiar with. So what I'm going to do here, the 2p, I'll put at the highest, 2s I'll put down here, and the 1s at the very bottom. That's the lowest energy. And I'll do the same for both sides. Okay. There's all the electrons for nitrogen, or all the orbitals for nitrogen. Remember, every bond has 2 parts, the lower energy bonding and the higher energy anti-bonding. So I'm going to draw those in for the 1s. It's going to look just like what we've been doing. Okay? Remember, the 1s orbitals are spherical. So when they come together in bonding, it will look like this. When they come together in anti-bonding, they'll be opposite phase, or destructive interference. And so we name them the sigma 1s and the sigma 1s star. Hopefully that should look identical to everything you've seen before as far as molecular orbitals. The template's going to look the same. 2s is going to look actually just like the 1s. There's going to be the lower energy and the higher energy molecular orbital. This should be looking exactly like what I'm drawing below. The 2s orbital, only difference is the sphere is larger because it's 2s, so it's a slightly higher, larger size. But otherwise, the diagram will look identical. The lower energy is the bonding part, that's the sigma 2s, and the higher one is the sigma 2s star. Let's zoom in on that part so it's easier to see. Okay? So that's the bottom half. This should look exactly like the lithium picture we drew just a moment ago. Bottom half is totally identical because this is the identical part of the electronic structure, the 1s orbitals and then the 2s orbitals. I haven't done the electrons yet. Is there a question? Yeah. On the exam, she's asking, do we need to draw the atomic or molecular orbitals? That is the circles? No. These here? No. None of these have to be drawn. I'm just drawing it now so you see where things come from. Once we draw our first MO with 2p orbitals, which is this one, that'll be the last time I draw this. It's just so you can see where things are coming from, so it doesn't look as random as it could look. Okay. Now, the 2p orbitals make their diagram look different because the 2p orbitals are not spheres. There's these two-leaf clovers that look, one looks like this, another one is the same but going forward and backward in the page, and then there's one that goes left and right, like that. And so I'm going to draw, same over here, there's one that goes up and down, there's one that goes forward and backward, and then there's one that goes right and left. Okay? So there's all the p orbitals. That'll cause the molecular orbital, or the center part, to look differently. Okay, so it's going to be a little bit different for the nitrogen. Okay, first, can you see that this one and this one can come together in a bonding fashion where they just come together like this, these two. And it would look like this. This would be bonding because the unshades are together and the shades are together. And in an identical way, these two could come together. They're in and out of the page, but they would fly together like this. Okay? Those two would actually be identical looking and thus cause two energy levels to be down here. Like this. Okay, let's figure out the name of these molecular orbitals, or those energy levels. Is this going to be a sigma? When you look at this, is this a sigma or a pi bond? It's called a pi bond because the bond happens, let's see a different color here, above and below the center point. Above and below. So this is called a pi bond. What do you think would be the subscript? Yeah, since it comes from 2p orbitals, it's called a pi 2p. And that's a bonding interaction. There's actually one more bonding interaction. If you take these two right here, where my fingers are, those two will come together in bonding. Zoom in a little bit. And that would look like this. When those two come together. It's the only one like it. There's no other. Now we've got, since there was 3 from each side, those are the 3 bonding interactions. So for this one right there, the one I just drew right there, is that a sigma or a pi? Sigma. That would be a sigma. You can see the bond or the overlap occurs between the center. So it's occurring right here if you watch my pen, right here, between the centers. So this is called a sigma, what do you think the subscript is? 2p. Okay, the anti-bonding would be just above that. So all three of these will have anti-bondings. Oh, this is blue. Blue will look like this. So we'd have the pi, that's in black, the pi 2p star right there, and the sigma 2p star, which would look like this if you wanted to draw it out. Again, on the final, you don't have to draw out these lobes. It's just so you can see it here in class. Here now shades and unshades are together, so that's an anti-bonding. And this is a typical picture for p orbitals right here. It looks weird when you first see it, but after a while you're going to say, oh, it always looks kind of like this. So if it always looks kind of like this, you're not surprised the next time you see it. It just looks shocking the first time you see it. So the lowest energy is pi 2p. The next one is sigma 2p, and then pi 2p star, sigma 2p star. Mathematically, we could actually calculate these energies so you see why they are where they are. But essentially, the intuitive argument is the more overlap, the lower the energy in the bonding. And so that's kind of intuitive. But as far as which one goes next, that you'll more have to remember. Yes? Second, is the PZ do the sigma bond? I believe so. I don't recall. Okay, now let's fill in the electrons. So, for each nitrogen is 1s2, 2s2, 2p3. So it's 1s2, 2s2, 2p3. And the same for the other side. 1s2, 2s2, 2p3. Let me show a big zoom out of this so you can see it. So I filled in the electrons for nitrogen on both sides, according to its electron configuration. Kind of see everything. And now let's fill in the electrons in the center. Do each diagram separately. So for the first one, 2 electrons from each side over a total of 4 in this bottom picture. 1, 2, 3, 4. For the second one, 2 electrons in each side for a total of 4. 1, 2, 3, 4. That's the same as what we saw before for lithium and the other examples. The newest example now is up here for nitrogen with the p orbitals. 3 electrons on each side. So that'll be 1, or total 6. 1, and now watch. The other one goes by itself. The number 3 goes there, it pairs. Number 4 goes here. And now that's full, and so now it's going to go up to the next energy level. 5, and then 6. There's a total of 6 electrons that go to bed. Okay. Now we ask our common questions. First of all, is this para or diamagnetic? This would be diamagnetic. Everything in the center part is paired. So we call this diamagnetic. The second thing we ask is what's the bond order? Okay, look at the topmost picture, the 2p picture. How many electrons are in bonding molecular orbitals? Should count 6. 2, 4, 6. They're all in the orbitals that are lower energy. How many electrons are in the anti-bonding molecular orbitals? Should say 0. There's none up here at the top. 0. This turns out to be 3, and we would call that a triple bond. In this case, this agrees with Lewis structures, which would say that N2 is this structure there that I just drew in the bottom right-hand corner. It has a triple bond. We can't draw Lewis for all the things that we can do an MO diagram for, but in this one we can. That's N2. Now, on a final, you would draw more something that, if there's no questions, on a final, you would see a picture that looks like this. Okay? Why are the 1s electrons not there? It's a poor electron, so I don't need to include it if I don't want to. You can, but you don't have to. So notice the 1s is erased. Okay. I don't have the electrons filled in here, but what you would want to be able to do is to know all these, label all of these levels, the sigmas and the pi's. So make sure you are able by yourself to label these. This MO diagram works for everything up to nitrogen. When you get past nitrogen, I explain it because of a size issue. Is oxygen larger or smaller than nitrogen? It's smaller, and so there happens to be a change in energy levels once you get to oxygen. And there's pictures like this in your textbook. This is on page 419. In the reader, you'll see pictures like this on page 103 and 104. Okay, what happens in oxygen is the diagram changes a little bit. And let me show you how it changes. You can kind of see both of them at the same time. Okay, once you get to oxygen and above, it changes a little bit. You see what changed? The energy level between the sigma 2p and pi 2p have flipped. So these two flipped with these two. That's the only difference. Those two flipped. Okay? You have to remember, so it'll be up to you to remember that between nitrogen and oxygen, these diagrams flip. So the energy level between the sigma 2p and pi 2p flip. So that's up to you. You got to keep that in your brain. Otherwise, as far as the template, it doesn't matter what atom it is. You just fill in the electrons accordingly. So for fun, let's do this for oxygen. Okay? And we'll do it as we would do it for an exam. So if I wanted to do O2, I would write both atoms on either side, and I would draw a y-axis energy level scale. Then I know oxygen is 1s2, 2s2, 2p, 4. 1s2, 2s2, 2p, 4. By the way, I also know the Lewis structure for oxygen. It's this. That's the Lewis structure. You draw it out. So I'm going to expect at the end to get a bond order of 2. We'll see what happens. Okay, now, I'm going to put these orbitals in. So there's the 2s and the 2p. You notice I skipped something. I skipped the 1s. Why? Yeah, it's a core electron, so I don't have to draw it if I don't want to. Okay? On the final, you don't have to draw the core electrons for the MO diagram. The reason is they're not as involved chemically. So, let's do this. The 2s has a low energy and a high energy, or the bonding and the anti-bonding. Remember, every bond has two parts. The low energy one is called sigma 2s, and the high energy one is sigma star 2s. Now, according to what somebody over here asked me, I think you agreed to ask me, we're not going to draw the orbitals. You could if you wanted to, but that's not real required. So, and you'll see the book doesn't do that either. Most people don't do it. They just assume you know it magically. Okay? But I wanted to draw them just so you can see it. Okay. Then for the 2p, what I'm going to draw now It looks pretty similar to the neon, but now I know, oh, I'm oxygen or higher, oxygen specifically, so I'm going to draw this template right here. I'm going to draw this right here. So I'll repeat that in my picture here. Draw the dots, kind of beautify it a little bit. The lowest energy is the sigma 2p. The next is the sigma, or the pi, sorry, pi 2p. Then the pi 2p star. And then the sigma 2p star. You might be wondering, how do I remember which one is which? This is the way I do it. First of all, below the midline, that's the sigma 2p and the pi 2p, there's no stars ever. The stars are always on the ones above. The subscripts are all the orbitals they come from. So in the bottom picture, the subscripts are 2s, top picture 2p. And then here's a little secret. If you see one line in the middle all by itself, it's a sigma. Notice all those single lines are sigmas. If you see a double line, two lines right in a row, that's always going to be a pi. So that is an easy way to remember which one's which. The pi's in this case are these two right here, and I remember that because there's two lines. Let's fill in the electrons. It's a 2s2, 2p4. 1, 2, 3, 4. And same on the other side. 2s2, 2p4. 1, 2, 3, and 4. We fill in electrons one section of the diagram at a time. So the bottom set goes like this. There's a total of 2 from each side, or 4. 1, 2, 3, 4. For the top diagram, there's 4 on each side, or a total of 8. Now, if you're not good at filling these in, you should watch my pen. It's going to go 1, and then 2. Then 3, and then 4. They're both unpaired. Then 5, and 6. Now we're going to jump up to the higher ones. 7, and then unpair 8. Okay, so that's how you fill them in. Okay, magnetism. What's a magnetism? Paramagnetic. The reason why, there's unpaired electrons in there, specifically right up here in the pi 2p star molecular orbitals. That's why they're paramagnetic. Bond order. Look at the topmost section of the diagram. There's how many electrons in bonding molecular orbitals? You should see 6. These right here, 2, 4, 6. 2, 4, 6. How many electrons in anti-bonding molecular orbitals? You should see 2. These 2 up here in the pi 2p star. 6 minus 2 is 4 over 2, or 2. Tells us a double bond, which agrees with what we know from Lewis. Okay? Any questions on that? Okay, I understand that your brain is overloading and about to explode. Imagine the other classes right